Okay, cool. Thanks, Garrett. So I'm Derrick Higgins. Hi, everybody. So I am Senior Director of Data Science at Blue Cross Blue Shield of Illinois. And I also teach in the Computer Science Department at IIT. And this, what I'm going to talk about today is sort of a little bit of a fun side project that I did out of practical purposes, as you will see, and I thought might be just useful to talk about with the broader audience. Fair warning, it's not what I would consider like a heavy duty machine learning talk or anything, but there is a little bit of technical stuff in here, mostly just probability theory that can be a little bit difficult to decode, but I'll try and step through it and encourage you to stop me or slow me down if I'm doing things that don't make sense. Okay, so again, this is sort of on the teaching side, and the basic focus here is academic integrity. So in my course, I use multiple choice exams, and no matter what sort of assessment you do, it can be a challenge to just make sure that everybody gets evaluated fairly, that students aren't communicating in ways that they shouldn't during class, and it's not really fair to students who are working hard and independently for students to be looking at each other's papers or working together in other ways. And we don't want to do stupid stuff like this. This is a photo that came out. Was a student took this in class in their university in Thailand in 2013. Professor, because of precisely these kind of issues, forced all the students to wear these stupid little hats that shield their eyes so they couldn't look at their neighbors' papers and so on. That's that's demeaning and disrespectful, and nobody wants to go that route. So we want to make sure that we are that we have an environment of academic integrity, but also do that in a way that is respectful of students. So, I mean, maybe you're thinking, why use multiple choice tests at all? Multiple choice tests are stupid. We should do some more meaningful sort of evaluation. And I'll tell you why. You don't have to agree with me, but I do have a rationale for why I use multiple choice tests. I actually worked for a long time at the educational testing service that makes a lot of tests. So working on educational applications of natural language processing, like it sounds like one of our participants, I think Aaron, is working on now. So my team at ETS worked actually on how to analyze open-ended responses, so essays and spoken responses on tests like GRE and TOEFL, to either try to score them or route them to raters in certain ways. So I kind of understand the trade-offs between multiple choice questions and more open-ended, sort of what they call constructive response questions. And the nice thing about multiple choice questions is you can give people a lot of them in a very short period of time and measure a lot of breadth of knowledge. And for my classes in computer science and NLP, there are a lot of concepts that we expect people to take out of it. The scoring is objective, reliable, and easy. You can go through and use your scoring key. Whereas in the case of open-ended questions, there's this subjective element that the professor has to read it and understand it, and come to some understanding of how good the product is that you've created, and show the same professor the same artifact twice, and they may not come up with the same score, right? So there are a lot of advantages to multiple choice questions. I think that the balance is kind of shifted over time, where a lot of these tests used to be more multiple choice. They shifted to be more constructed response, have more essay questions, partly because we wanted to incentivize more teaching of writing and so on in the classroom. But now you'll see the SAT actually just dropped its essay section as a response to some of the reduced utilization during the pandemic. So I think that, at least for my class in natural language processing, you can get a pretty good understanding of what students know and don't know using well-constructed multiple choice questions. Here are a couple of example questions from my class. I don't know if you feel super confident that you master this material. Maybe you want to put the answers in the chat and we can all appreciate your knowledge. I'll just go through them here quickly. The final layer of a neural network uses a softmax activation function as its nonlinearity. So which of these following vectors could be possible output from that softmax layer? Select all that apply. So we get a vector of 1/3, a vector of 1/2, a vector of -1, 0, 1, and a vector of all zeros. So pause for beat. People think about that. And the answer is A. So it's a softmax, so it's a probability distribution. The values all have to add up to 1, right? That's the concept that we're measuring here. Number 2, for which of these tasks might a bag of words representation be a reasonable modeling choice? So like all that apply. So dependency parsing, context-free grammar parsing, part of speech tagging, machine translation, or none of the above. Unfortunately, I can't see the chat, so I don't know if anybody's answering correctly or incorrectly. And the answer is none of the above, because a bag of words representation for a text is going to lose all the information about the order of words, and so you can't use it for things like machine translation that are, where it's really all about how the words are put together in order to create some meaning. Okay, so this is the background. Multiple choice questions for NLP. And so the title of this talk here is a generative model for multiple choice answer copying. And so real quickly, I want to go through the difference between generative and discriminative models in machine learning. Often we talk about discriminative models, or that might be the only type of models that people are familiar with, but in natural language processing, especially, generative models are quite common. So let me talk here about the difference. Discriminative models are the standard sort of predictive machine learning models that you might be familiar with. So a random forest, a logistic regression model, you have some data that's your X variable, and then you want to estimate the probability of some target variable Y based on that observed data. So you're estimating essentially a conditional distribution. What is the probability of that Y given some X's? Generative models, you can get to the same place and have sort of a conditional distribution come out of it, but fundamentally they are modeling the joint distribution, the distribution of the Y's together with the X's. What's the likelihood not of some label given some data, but what is the probability of the label together with the data? All right. Typical discriminative machine learning models like logistic regression, you have to train them in a supervised way. You have to have labeled data. You have to have a bunch of X's that are paired with Y's as inputs to your model in order to do training. You can train discriminative models in a supervised way as well, given labeled data, but you can also train them or fine tune them in an unsupervised way. If you just have the X's and you don't have any Y's, you can train your discriminative model based on that unlabeled data. And the last difference here is the way that we get to what we really care about, which is making a prediction of a Y, a prediction of a label for a given data point, given X, in the generative framework, is based on this generative story about how we get the X's from some Y's that are latent and unobserved. And there's no concept of this in the discriminative world. So we tell ourselves that there is some process that underlies all the data that we see, that really when we see some text, it's generated from some unobserved label, and then we can sort of do backward inference from that to determine what the most likely label is, given the data, the X's or the words that have been generated based on that unobserved latent variable. So specific examples of generative models that you might be familiar with. Like I said, they're pretty common in natural language processing. One would be naive Bayes. If you're familiar with the naive Bayes text classification model, it has that generative story that I just gave you, basically. Where did text come from? We make up a story for ourselves about where a text comes from when we want to do text classification. We say, if you see this text, here's how it came to be. There was some label that represents its category, like maybe it was sports. And then based on that label, all of the words got filled out one by one. And they were all all of the words were generated such that they have high probability given the sports category, right? Similarly, latent Dirichlet allocation is another type of model that's used in NLP and is generative in nature. Again, we're talking about generating text according to some story. The story is a little bit more complicated in the case of LDA than it is in naive Bayes. Instead of randomly choosing a topic for a word or a label, sorry, a topic for a document or a label for a document, you're going to choose a topic distribution for a document, and then for each location, for each word location in a document, randomly selecting a topic from that distribution over topics, and then randomly selecting all the words to fill out the text that are conditional on the topic that's been selected. So it's sort of a two-stage process. So there's a large family of these generative modeling frameworks that are used in NLP and other fields of statistics as well. So just to go a little bit deeper into naive Bayes as a generative model. So again, Y is the document category or the label, and X is the multi-set of words in a document. The same word can occur multiple times in a document. What we're really trying to get to is a model that will allow us to predict the label for a document given the words, this X. And we do this by calculating the joint probability of the label and the words. So what is the probability of the text category being sports, for example, together with all the words that occur within that text. And then we normalize it by this quantity on the bottom, which is just the sum over all of the possible labels of that joint probability. And that gives us the conditional probability. But the fact that it's got this joint probability here in it, that's what makes it a generative model. So we can break down that joint probability, the probability of the label and the words, into two different pieces here. The prior probability of the label, which is this P of Y equals small y, and the probability, the conditional probability of the data given the label of the document. So that's P of X given Y. Right. And then we can further break down that second part, the probability of the data given the label Y, is the product over all the words of the probability of each individual word given that category of the document. So we're just assuming that words occur independently in a document conditional on the label. And there's otherwise no structure to documents at all. So again, the generative story here is we randomly choose a document category that corresponds to this P of Y at the left-hand side, the prior probability of the document category. And then we randomly choose words for each document based on that category. So that's how that plays out as a generative model. All right, just to point out, there are generative models outside the NLP world as well. One example of a generative model you might be familiar with is a Gaussian mixture model. So just like for naive Bayes text classification, we randomly choose a label for a document and then choose all of the words conditional on that label for the document. In the Gaussian mixture model world, we're going to randomly select a cluster to start with, one of K clusters, and then randomly select a point in the neighborhood of that cluster center according to some normally distributed density function. So that's the generative model that underlies GMM. And now I'm going to talk a little bit about how we can use this generative model framework for wrong answers on tests. We're going to tell ourselves a generative story about where wrong answers come from when students are doing a multiple choice test. Let me just pause there and make sure if there's anything I can clarify. There's an opportunity to do that. Okay, moving ahead. All right, so again, we're going to use it. We're going to make a generative model, and the generative model, instead of being a model of where documents come from or where points come from in some space, if we're talking about Gaussian mixture models, this is going to be a model of where students' pairs of wrong answers to test questions come from. So a little bit of terminology before we move on here. We're going to use this capital S to represent students. So S1 and S2 are two different students. We're going to have a set of questions that we're talking about. It's capital Q here, the questions on the test. And then the answers are going to be represented by capital A. So capital A super S1 is going to be student 1's answers. Capital A super S2 is going to be student 2's answers. Right? And then we can use this Q minus to represent the questions that one or both of these students got wrong. So Q minus is the set of questions that were not answered correctly by both students. So the question is, can we create a generative model that defines the distribution of these answer pairs? So the expression here in the middle of this slide is a little bit complex. It's basically the set of answer pairs such that the question that they're answering belongs to this set of incorrectly answered questions. So it's a lot of terminology, but it's really just like the pairs of answers from two students that are at least one of which is incorrect. Right? That's the set of observations that we need to explain with our model. And so the rationale here for choosing to just talk about incorrect answers is that if they both got the same correct answer, we don't really want to hold that against them. You know, we're gonna give them the benefit of the doubt and say, if you got the same correct answer to a question, it's probably because you know the material. It's not because you're copying. Right? Okay. So here's the generative story that we're going to go with for this model of wrong test answers. For every student pair that we're considering, we're going to randomly choose a class that defines how they're interacting, either copying or independent. So the copying class is they're colluding in some way and one student is copying off the other. The independent class means they're working independently. And if the students are working independently, then our story is going to be, well, their answers are generated independently. So each student's answers are drawn from some question-specific distribution. So, you know, if the question 5, half the class answered A and 25% answered B and 25% answered C and 0% answered D, that's the distribution that we're going to randomly choose from when we consider the probability of these students' answers occurring together. If students are copying, though, if this Y variable is set to copying, then the story is different. Then the first student's answer is going to be generated from this distribution, this question-specific distribution, but the other student's answer, some percentage of the time, is just going to be completely copied over from the first student's instead of being generated independently. So there's this alpha parameter that says, you know, alpha percentage of the time that first student's answer is just copied over, and then 1 minus alpha percentage of the time we back off to that independent strategy where the student is you know, legitimately answering the question on their own and we're using that question specific distribution to model it. Okay, so that's the story, and now we have to put that story into probabilities. So first two lines here are really just basic probability theory. If we want to get the probability of X, the probability of some data, that can be defined as the probability of X and Y plus the probability of X and not Y. That's just an axiom. And we can expand both of those quantities, both of those joint probabilities on the right. So probability of X and Y is equal to the probability of Y times the probability of X given Y. And the probability of X and not Y is equal to the probability of not Y times the probability of X given not Y. So that's, again, just a rewrite of the line before using the definition of conditional probability. And we can apply this in the specific case of our generative model for copying, because the basic thing we want to calculate is what's at the top here. This is the expression before. What's the probability of a bunch of paired student incorrect answers, right? And the answer is, well, we can break that down into two parts. It's the probability of the incorrect answers occurring with independent work, plus the probability of those incorrect answers occurring with copying, right? So that's sort of the analogy between the expression above and the rewrite below. Okay. So this is an attempt to turn our generative story into some more explicit probabilistic expressions here. So again, we've got these prior probabilities here, the prior probability that students are working independently versus the prior probability of them copying from one another. This represents the first aspect of our generative story, that when students are working independently, their answers are generated independently, so you can just multiply the probabilities together. So we're taking the product over all the questions of student one's, the probability of student one's answer to that question times the probability of student two's answer to that question. That's how we get the probability of the entire answer set. And then for the under the copying scenario, things are a little bit more complicated. Again, we're just using the question-specific answer distribution for student one probability for a given answer. And in the case of student two, we're using this hybrid strategy where alpha percentage of the time, if the probability will be 1 if student 1 and student 2's answers agree because they're copying, and 1 minus alpha percentage of the time, the probability will be equal to the question-specific distribution probability for that question because they're actually working independently. So that's the math that corresponds to our story. Right, so this part here is the conditional probability of answers given that Y, the target category, how students are working together, is independent, and this is the conditional probability of answers given that students are actually colluding or that Y is copying. Okay, so where we want to get to is making some determination, are students copying or are they not copying, right? So the thing we really need to compute here is the probability of Y equal to copying given the student one, student two answer pairs. And we can calculate that as the probability of Y, of the joint probability of Y equals copying and the student answer pairs divided by the joint probability of the data there, the answer pairs observed. But we don't really need to do that. We don't really, we need to actually know the prior probabilities of copying and working independently to do that. Instead, we might just ask, how much more likely is it that the answers were generated through copying compared to independent work? So just taking the ratio of these two different conditional probabilities, probability of the answers given copying, probability of the answers given independent work. And to do this, we only need two things. We need to decide on this alpha hyperparameter, which is a little bit subjective. Like if somebody's copying, what proportion of the answers do they actually copy? Do they copy all of them? Probably not. Do they copy 50%? Maybe, I don't know, 30%. I guess it depends on the person. So the way the model's set up, we just have to choose a value. And in my experience, 80% here works pretty well. If you just assume that where there's copying, 80% of the time, the student will be getting their answers from the person they're copying with. And then we need to know these question-specific answer distributions. So for a given question, question 5, how often do students select A, B, C, D, so on? And these things, given a large enough class, you can just sort of calculate from class response frequencies. So we do this, and then you can calculate our statistic of interest, which is the ratio of the probability of the answers coming, probability of the answers given the copying hypothesis to the probability of the answers given the independent work hypothesis. And on this graph, I'm actually going to show the base 2 log of that. You can calculate this statistic for all pairs of students in the class, and you generate a heat map like this. And you can see, for most student pairs, the answer is the statistic is close to 0. Their answer patterns are really not that similar. But for some students, they're pretty high. If the top of the scale is 20, that means under the model, the probability of their answers resulting from a copying hypothesis is 2 to the 20 times more likely then the probability of their answers under the independent work hypothesis, which is suggestive, right? So, okay, and it's suggestive, but it's not. We should also bear in mind, what this means and what it doesn't mean. I definitely don't. I'm not out to get students or want to. The last thing I want to do is create problems for students who don't deserve it. So we should recognize the limitations of this model, right? It's models and approximation to reality. There's a lot of stuff that's not captured here, right? Students might get the same wrong answer for other reasons besides cheating, right? Maybe they studied together and they learned the same wrong thing, which they're both putting into practice on the test, right? Another thing is, there are assumptions in the model that every student is sort of answering questions according to the same distribution. They're just sort of rolling a die to choose what answer they're going to choose for each question. And of course, that's not true. Different students know different things. Probably, students who master the material more fully are going to have a different answer distribution than students that are lower down. Again, we're sort of ignoring correct answers here out of a desire to make sure that we're fair to students, but it's probably true that students who share a lot of correct answers, that might be some sort of evidence in favor of an academic integrity problem as well, even if it's not as strong. So again, it's really about likelihood, not about definitive findings or proof. And this kind of stuff is best considered as something that you use in conjunction with other types of information. What happened in the classroom on that day, what has the experience been with these students throughout the semester. So it's definitely not something that that it should be used in a rash way on its own. Okay, that's what I wanted to share today. Also, if you're interested in the code or the method, it's out there on GitHub. You can screenshot this and use the QR code to actually look at the code and see how it works. Once again, I do work at Blue Cross Blue Shield, and we have a lot of data science work going on there that folks might be interested in. We're doing hiring. We're especially interested in bringing on data science product managers who can drive data science work toward business results, and data science engineers who can help us with the infrastructure and the technical quality of the models that we develop. Thanks.
Great, thank you, Derrick. So we have a few questions in the chat. Do you have access to that?
Oh,
I can read them otherwise.
I think if I stop sharing, I don't know how to find chat. Where's chat? More chat.
I can ask. Okay.
I got it.
I'll just read them off. It's easier. So from Jua, I'm sorry if that's probably not how you pronounce your name. Jua Wang. Can you talk about some case studies of NLP in insurance?
Yeah, I can. So one thing I can talk about, there's sort of a family in use cases in my world right now around electronic health records. So you're probably aware that there has been there's been incentivization of adoption of electronic health records by healthcare providers and greater interoperability and open standards for health data sharing across organizations. That's still very much a work in progress. But a lot of providers are using electronic platforms to collect information about health encounters and so on. And that is useful for them internally to do analytics on their patient population, figure out how to support them. Case in point, COVID-19, you want to know who has risk factors that have been identified by the CDC as potentially leading to worse outcomes for COVID-19. That data will allow you to mine that and make sure you reach out to the right people for vaccine distribution. Similar use cases on the insurance side, where the electronic health records are shared with us for many types of interactions that we have with providers. And using that data allows us to respond appropriately. If it's a prior authorization request, we can use some of the information in the health record to determine, can we auto approve this and just not subject it to manual processing at all. Similarly, we might use it for clinical applications to figure out which of our members we should be reaching out to let them know about COVID vaccine availability. So a lot of things are driven by electronic health records. And then I'll say one level back from that, there's a lot of health records that we get that are not yet in this HL7 or easily parsable format. There are a lot of things that are still faxed to us or sent as image attachments to emails. And there we have to do some sort of OCR first in order to extract the text that we could use for all these downstream applications.
Hey, Derrick, Ravi here.
Hey, Ravi.
Can you go back a few slides? I just want to understand the formula which you had given. Actually, a couple of more.
Okay.
Yeah, right here. Actually, so the first formula, the probability of, can you explain the formula before the equal to sign? I understood the formulation.
I know it's very notation heavy. I'm sorry.
Yeah.
The basic concept that's supposed to be represented here is the pairs of all answers from two students, S1 and S2, that are not correct. Right?
Oh, okay. Okay, I got it.
So like the part between the square brackets is answer pairs, student 1, student 2 answer pairs, all of those. And then after the colon, it's such that the question that corresponds to those answers is within this Q minus set, which is the stuff that they got wrong.
Oh, okay. So you're basically assuming when they get it right, both of them, any two student pairs, they are most likely to be the independent answers.
Right, that's the assumption of this model. We don't even care about those correct student answer pairs because that's just no information at all about whether they were colluding. That's just, they're good students and they got them right.
Okay, got it. Okay, thanks.
Yep.
I have one additional question here related to that. So that assumption that's being made that correct answer pairs are not helpful information, is that I've been trying to think through that. Is that an assumption that is made in some form of a logical or proof sense, or is that just what you've encountered by interacting with the data and realizing that it isn't helpful information?
No, it's not that it's not helpful, or it's not that I believe it's necessarily true in a strong form. It's just like, I think it's driven by a desire to make this methodology more defensible and fair seeming. So if you're sort of using it against students that they got the right answer, that somehow seems wrong, and like you could see how they would object to that with some cause.
So Derrick, the probability here, can you hear me?
Yeah.
Okay, so you have quite a bunch of probability, and are you assuming, you must be assuming some probability distribution because that's generative model, right?
Right.
So what kind of a distribution are you assuming for? You can give me some example, like the prior, like.
Yeah, well, yeah. So this is the conceptual version of the model, which is not to say it's necessarily how the code works. So I'll skip. So you'll notice that I skipped past the priors because we're actually not computing this probability at the end. We're computing this ratio instead of this ratio of the where'd it go? There we go. Instead of computing the thing on the top, this probability of copying given the answer pairs, which does require the priors, we're actually computing this ratio statistic, the ratio of the two conditional probabilities that doesn't require the priors. Again, that would be a subjective decision. Like how do you know what the likelihood of what the prior likelihood of a given student pair colluding is? I don't know. Like hopefully it's small. So it's really more a matter of trying to rank students and produce some usable metrics to flag things rather than to truly
okay.
define the probabilities. But we do need to sorry, I'm trying to get rid of the stuff on top of the equations. We do need to fill out some of these values. So we need the alpha, which again is made up. You know, what is the likely, if somebody's copying, how many of these answers do they actually copy? You know, I say 80%, you could say it should be 60%, and I couldn't really argue against you. And we need these question-specific distributions, this P of A sub I, like what's the likelihood of, and that's just a categorical distribution. Right? So probability associated with A could be 50%, probability associated with B could be 25%, C could be 10%, D could be 15%. So it's just a categorical distribution.
So you don't, I guess you're assuming some probability distribution, like for the PI, AI, S1.
Correct.
So if you can share with us, what kind of a assumption are you making? Bernoulli or maybe not?
Well, it's just a categorical distribution. So it's derived by maximum likelihood estimation from the student response data for the class. So you just like, if half the students said it was A, then A has 50% probability.
So you don't assume you know the format of the distribution, you just estimate the parameters, or?
Yeah, it's just bootstrapped off the data.
Okay. Okay.
So it won't work well if you have a class of 10 people.
But
so Derrick, one more question. If we actually pick a prior for alpha, and then is there a way we can actually confirm that based upon the whole Bayesian one? Like, is that prior coming close to what's in reality? That is kind of the way you kind of evaluate your Bayesian network,
Mm-hmm. Yeah, I'm sure there's a lot more sophisticated things that you could do in a generative modeling framework, using sampling approaches to parameter estimation here and trying to get some uncertainty estimates for things like alpha for sure. But I haven't done that. This is all just point estimates.
Okay.
so Derrick, do you need to estimate the parameters for the different probability distributions?
You mean the answer distributions?
Well, you have a lot of distribution here. I mean,
It looks like it, but it's really just one. I mean, it's one distribution for each question, right? For every question, there's some distribution over the answer space. And that just comes from the student answers to that test.
Okay.
Yeah, I is, I think, the number of questions, basically. Is that correct? I'm forgetting the
Correct.
notation, sorry. Yeah, okay.
Yeah,
okay.
I ranges over the number of questions, yep.
Okay, got it.
I have an additional question that also has a kind of follow-up to it. So this model is about multiple choice questions is specifically geared towards academic integrity problems. I'm curious if you've worked on any multiple choice related models for non-academic integrity or other issues. The reason that this came to mind is because I think in high school, one of my teachers used, I looked this up just now, the point biserial coefficient, which is essentially an indicator that measures the correlation between specific questions on a test to the overall score that students get on that test. So if a student does really well, or if a question has a mix of students doing well on the test and poor on the test, and the question has a mix of answers from both, it's probably a bad question. You should throw it out. I'm wondering if you've worked on anything similar to that, maybe more robust than a point biserial coefficient.
Yeah, no, well, not that exactly. I would say I have some familiarity with a lot of the methodology for analyzing multiple choice tests, just because I worked at a testing company for many years. And so I had a lot of colleagues who were psychometricians and they know about a lot of this stuff. And yeah, so there's like item response theory that people use, which is a parametric model that people use to summarize the characteristics of test items, like how hard are they, and how well do they kind of divide between students who know a lot, and or like how reliably do they divide students at different levels. And that, that's a kind of kind of model in that space. And there's other methodology that people do around test fairness, where they do things similar to what you said around point by serial, where the question is, given looking at particular subgroups of students, like men versus women, or different racial and ethnic subgroups, and how they perform on specific items, and how if you sort of divide students into cohorts based on their overall test performance, whether you see differentiation for specific items between those ethnic groups. So yeah, I have more passive knowledge of some of that stuff, but yeah, I haven't done any work on that.
Interesting.
So Derrick, do you have a counterpart model from the camp of discriminative models? I mean, I understand for generative model, you usually have stronger assumption, but it's easier for your calculation. But for the discriminative models, you have a weaker assumption, but it's more robust, but more computation. Do you have I guess there are some models from the other camp, right?
Oh, absolutely. Discriminative models, I have nothing against them. And, still in real life, probably 95% of what I do is in the discriminative frameworks. It's not that I don't like them. It's just the big limitation is discriminative models need labeled data, and we don't have a nice labeled data set that says these are the students who we're copying and these are the students who we're not. That would be really hard to collect. So we kind of, well, if we had such a data set, we could certainly use other methods for this problem. That I just don't anticipate getting one anytime soon.
Good, I see. Thank you.
Sure.
So other than other than the GMM, what are the other generative models in NLP?
In natural language processing?
Yeah.
So like in the speech world, you would have a Gaussian mixture model for like textual features, but yeah, so naive Bayes, LDA. In the sequence labeling world, things like hidden Markov models are generative models. What else? There are like generative parsing models as well. So like Eugene Charniak had a generative model that for phrase structure parsing, but that's not really a well-known thing. I mean, there's just there are different things that people have built for specialized purposes that are generative in nature.
Okay. Thanks.
So Derrick, I just want to clarify. I know you have a background in NLP, but looks to me this problem you are presenting doesn't have anything to do with NLP, right? You just know the answer, right? Yes. I just want to make it sure, right? It's not NLP at all. You know the answers. It's just multiple choice, right?
That's correct. So.
Okay.
Yeah.
I could do different things sometimes. And like I said, it was driven by sort of personal practical need. So.
Do you have the data and the code, or just to see how the model worked out on the GitHub, or is it like there already, or because you didn't present the code actually, or the results basically?
If you go to the GitHub repo, you'll see there are some sample data sets that are in there. They're actually, so other people have worked on this problem of, I didn't do like a lit review as part of this, but other people have worked on identifying academic integrity issues with multiple choice tests and have used more of this IRT methodology that I mentioned before. That doesn't really work for this context because the IRT is much more data hungry, and you require a lot of student data in order to set the IRT parameters. So it works like if you're talking about an administration of a GRE test or something where you've got thousands of students. It doesn't work so well if you have a class of 50 people, something like that. So anyway, where I'm getting is, because there's this prior research and some published data sets, those are usable in the repository.
Oh, okay. Got it.
So Derrick, there's a question here from Omar, and it's related to the healthcare industry. He says, I work at Rush University Medical Center and work heavily with clarity data in Epic, generally clean data. In Epic, generally clean data. You mentioned an example with insurance and how data comes through. I'm assuming your data from providers is coming from different sources. Just curious, is the main challenge you face the source of data and being able to clean and blend together, or the business application of the data in a model such as NLP, trying to get an idea of bottlenecks faced in healthcare elsewhere?
Yeah, hard to localize. I would say it's both. So definitely there are challenges in sourcing, cleaning, integrating the data in a usable way, and then also the downstream modeling and integration with the business application. Yes, being a payer, we don't have a single electronic health record platform like Epic that is used internally. We get it from whatever system our provider partners are using. Epic is a big one, but there are other ones, and based on the the different platforms and the different ways that providers use them, the data comes in slightly different formats. Another challenge there is, if you're working with provider systems, you just have that electronic health record there all the time, and it's up to date based on the most recent interaction that the patient had with their doctor. Whereas we, as payers, we get whatever snapshot was sent along when there was a need for some for some interaction with the payer. There's a billing issue. There was a prior authorization request. So we have to figure out what snapshots of data we have for a member and how best to integrate that into a holistic picture at a point in time. Really challenging.
Okay, any other questions for Derrick? All right, well, with that, I'm going to stop the recording. Thank you, Derrick, for a great presentation.
Yeah, thanks, Garrett. Thanks, everyone.
And so we'll stop the recording here.